So hello everyone, today we'll solve some problem on Jordan canonical form. So before that, let us see what is Jordan canonical form and its properties. So as we have previously seen that a matrix is diagonalizable if and only if that is geometric multiplicity of eigenvalues is same as algebraic multiplicities of that eigenvalue, and this is true for all eigenvalue eigenvalue lambda of given matrix. In this case, this is diagonalizable. So A is diagonalizable if and only if this is true. But unfortunately, this does not hold always, right? So that's why what is the next best approximation we can make? Not diagonalizable, not diagonal matrix. That is diagonalizable means there exists some P which is invertible matrix such that P inverse AP can be P inverse AP. This can be made to the diagonal matrix, a diagonal matrix T. But this is not always the case. So, but we can do something like this. So, actually, why do we always try to make something diagonalized? Try to make something diagonal matrix. This is because of the fact that if something is diagonalizable, that means there exists some basis vector v1 up to vn for which the linear operator tv1 it is easy to see. For example, tv1 is something as c1 v1, tv2 is something as c2 v2. So the expression of this linear operator is easy to study in this case, but this is always not true. So what can be done? So that's why Jordan matrix comes actually. Jordan matrix. So what is Jordan matrix? Jordan matrix is it is made from some blocks. So let me give those names. For example, JK. So before that, let us define Jordan blocks. So Jordan blocks, it will take the form. This is called Jordan block. So this notation is different from what is given in Hopman-Kunze. So this is actually most used notation. So I will follow this notation. So it will consist some diagonal entries lambda, and there is another entry, non-zero entry, which will appear just above the diagonal entries. So there will be some lambda. So let me write something more matrices. Lambda, and so for example J4 lambda. There will be four those lambdas, and above those lambdas there will be one, and except those entries, all other entries are actually 0. So other entries will be 0, 0, 0, 0, 0, 0, 0, 0. So we'll always skip those zeros and we just write diagonal and the non-zero entries. And similarly, any jk lambda, it will take this form. Diagonal entries are actually lambdas, lambda, and just above the diagonal there will be some 1. Okay, So there will be 1 1 like this. This is actually called Jordan blocks, and any so let us create a block diagonal matrix made by those Jordan block. So block diagonal matrix made by Jordan blocks. So it will take the form like this. So let us denote it by J. J will take the form. There will be some JK1 lambda 1, and there will be another block JK2 lambda 2, etc. JKM lambda m. Those kind of block will appear, and except those blocks, every other things are actually 0. Okay. So those type of matrices are called Jordan matrix. Now, the interesting fact is that those a matrix may not be diagonalizable, but it is always true that there exists some P such that P inverse AP, this is some Jordan matrix. This is always true. So this is always true. And those P are from actually complete field, for example C complex number. Otherwise this is not true. Okay. So this is called diagonal like this. This is called Jordan. So every matrix can be made for every given matrix A. There exists some P such that it will take the form Jordan matrix. So that form is unique up to some rearrangement, because those blocks maybe those blocks can be interchanged for some cases. So up to this, those Jordan canonical form, this J, it is unique. Up to some rearrangement, this is unique for every matrix. And what are the properties can be obtained from this Jordan canonical form? So let J be a Jordan canonical form for A. Okay, that is P inverse AP equal to J. Then there are some properties we can get. Those properties are first note that those diagonal entries, for example lambda 1 and lambda 2, those kind of diagonal entries, those are actually eigenvalues, and algebraic multiplicities of those eigenvalue, algebraic multiplicity of eigenvalue lambda, this is actually same as number of times lambda appear in G. And another thing is, so this is same as sum of sizes of Jordan block corresponding to lambda. So for example, this is called Jordan blocks corresponding to lambda 1, because these blocks contains all entries where diagonal entries are lambda 1. Similarly, this is called Jordan blocks corresponding to lambda 2, and the size is given here. For example, it is J4 lambda. So this Jordan blocks has size 4, right? Similarly, it has size k. Again, we know that algebraic multiplicity is same as number of, that is multiplicity of lambda in characteristic polynomial, right? So this is same as multiplicity of lambda in characteristic polynomial of A. So if we factorize the characteristic polynomial, the highest degree, that is x minus lambda to the power k, that ki will be the algebraic multiplicity of lambda. And another thing, geometric multiplicity of lambda, this is same as number of uh, so number of Jordan block corresponding to lambda. Okay. Those are actually called algebraic and geometric multiplicity. And geometric, again, recall that geometric multiplicity is same as dimension of, this is defined to be a dimension of eigenspace corresponding to lambda, right? Other results are like this. So if from those two things we can say diagonalizable, A is diagonalizable. This is true if and only if that algebraic multiplicity of lambda is same as geometric multiplicity of lambda for all eigenvalue lambda. But now we note that those two are equal again. These two are equal, but sum of sizes of Jordan block and number of Jordan blocks, this will be only equal if and only if those Jordan blocks are 1 by 1 matrix. Otherwise, if something is, suppose some Jordan block is, it will look like something like this: 1 2 1 2. This kind of Jordan block. Then we can see the sum of sizes of Jordan block corresponding to lambda. This is actually 2. That is number of times the eigenvalue 2 occurs. It is 2. But number of Jordan blocks, this is a single Jordan block. Right? By definition of Jordan blocks, this is single. So 1 is not equal to 2. For example, let us write 3. Otherwise, it may confuse. So here, though algebraic multiplicity is 2, but we can see geometric multiplicity is actually 1, because number of Jordan blocks, there is only single Jordan blocks. Let me include another thing, then it will be more clear. So suppose there is another Jordan block which contains another 3. So now we can see that algebraic multiplicity will be 3, because there are 3 diagonal which contains 3. But geometric multiplicity will be 2, because there are only 2 Jordan blocks. This blocks is a Jordan blocks. There is another Jordan blocks 3. This 1 by 1 matrix. So geometric multiplicity and algebraic multiplicity, those will be same if and only if those blocks are 1 by 1 blocks. So that is saying same as those, that is those 1 cannot appear, right? So that we can again separate those two things. This individual, we can make individual blocks. So this is if and only if Jordan form of A is diagonal matrix. This is a diagonal matrix. So those must be 0. Therefore, this is actually diagonal, right? Because there is no 1 above the diagonal. Those are few properties which we will use during this tutorial. And another thing I should mention, this is property 1, 2, 3. Those are properties. Another thing is multiplicity of lambda. So we know that multiplicity in characteristic polynomial, that is sorry, multiplicity of in characteristic polynomial, that is actually algebraic multiplicity. It is already known. But what is multiplicity of lambda of some eigenvalue lambda in minimal polynomial? Sorry, minimal polynomial. This is actually highest or size of largest block appear in Jordan form. So, for example, if we take this Jordan canonical form, then we can see that minimal. So, minimal polynomial for this, it will look like x minus 3 whole square, because largest Jordan block, it is actually 2 by 2 block corresponding to 3. Okay, largest block corresponding to 3. Otherwise, it is corresponding to 3, corresponding to that lambda. Okay, those are some properties of eigenvalues, Jordan canonical form. Now let us solve some problems. So let us consider this problem. Here A is given, this A is this matrix. Then what will be the Jordan canonical form of A? Okay, let us try to solve this. So given A equal to 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, minus 4, 0, 5, 0. Those matrices are actually called companion matrix, and for those actually it is already known the characteristic polynomial. So in general, you know, companion matrix, those matrices, it will look like, it will take this form 0, 1, 0, 0, 0, 0, 0, 1. So let me put another 0, 0, 0, 0, 0, 1, 0, and after that it stop at 1. After that it will be minus C0, minus C1, minus C2 up to minus Cn. Then if we take this matrix, let me give another name B, then companion the characteristic polynomial of this B, it will take this form. It is C0 plus C1x plus C2 x square up to Cn x to the power. So this is actually the companion matrix Okay, let me put what is the, so it is n plus 1 by n plus 1 matrix, right? So it will end at Cn x to the power n plus x to the power n plus 1. Because it is n plus 1, otherwise we need to take n minus 1 here. So from here it is easy to observe that characteristic polynomial of A, chi A, usually it is already given in Hoffman-Kunze. You can look at this, and explicitly it is easy to see that explicitly you can just subtract B minus some, that is B minus xi, and take the determinant. If you calculate the determinant, it will explicitly it will take this form. So I am not calculating the determinant. Chi A, this is same as xi minus a, and if you calculate the determinant, it will take from here. It is easy to see that it will take this form: minus 4 plus 0x plus 5x squared plus 0x cube plus x to the power 4. Okay, that is characteristic polynomial. This is characteristic polynomial. Sorry, it is actually written as chi a of x. Sorry. It is easy to calculate this characteristic polynomial, and it will take this form: x to the power 4 plus 5x squared minus 4. And now if we factorize this, plus 4 plus 5, this can be written as plus 4 minus 1. This is, yes, this, so x squared plus 4 into x squared minus 1. So this is the factorization, and from here we can see that eigenvalues okay, is there any mistake? No. Maybe I have made some mistake. Let us look. So, sorry, just look at the sign. There is minus C0. That's why I have made some mistake. So, it should be actually, we need to take care of the sign. So, minus 4, that's why it is actually plus 4. This is plus 4 and 0. And then there is minus, there should be minus 5, but there is actually plus 5. That's why there will be minus 5. After that, it is okay. So x to the power 4 minus 5x squared plus 4. X to the power 4 minus 5x squared plus 4. Factorizing this we have x squared minus 4 into x squared minus 1. So therefore eigenvalues are, so solving this, equating chi a x equal to 0, we get, so this is again, this is same as, otherwise let me write x plus 2 into x minus 2, again x minus 1 into x plus 1. So from here it is clear those eigenvalues are actually minus 2 and then plus, sorry, this is plus 2, plus minus 2 and plus minus 1. Those are only there are 4 eigenvalues. Since those eigenvalues are distinct, therefore it must be diagonalizable, right? Since eigenvalues are distinct, because eigenvalues are distinct, therefore geometric multiplicity and algebraic multiplicity both are 1 in this case, right? And we know that this corresponding to distinct eigenvalues, so their eigenvectors are actually linearly independent. So we have enough eigenvectors. There are actually 4 eigenvectors. So we can always diagonalize because this is 4 by 4 matrix, right? So eigenvalues are distinct, therefore which imply it is diagonalizable. Algebraic multiplicity equal to geometric multiplicity for all eigenvalues. Because it is actually there are 4. It is so both should be 1 in this case because it is actually 4 by 4 matrix. It is 4 by 4 matrix. So all those are actually appearing. So it will appear 1 times only. It is diagonalizing. Take any lambda I. Those are actually same. Those are actually 1. So since it is diagonalizable, then Jordan canonical form must be diagonalizable. Means it must be diagonal. So what is the diagonal matrix here? We can see that this is diagonal. -1 +1 +2 -2 all appears, and others are not diagonal. For example, there is 1, so this is not diagonal or diagonal. Those are not diagonal. Okay, so this is correct and all are wrong. It is unique. This there must be only single answer. So let us look at question number 2. Here, linear operator T on a complex vector space phi, it is given, and its characteristic polynomial is x square x cube into x minus 5 whole square. So this is also those are actually questions from net or gate. So those are actually questions from net, and there are some also questions from gate. So x cube into x minus 5 whole square, this is the characteristic polynomial, and minimal polynomial is also given. Now we need to see which are possible and which are not. Okay, let us denote using that notation chi x, characteristic polynomial of t, or let me just denote it by chi x. This is same as x cube into x minus 5 whole square, and minimal polynomial mx, this is same as x square into x minus 5. So we note that minimal polynomial divides characteristic polynomial. And Jordan form of T. So okay, let us look what are the possibilities of Jordan forms. T is uniquely determined by the given information. So yes, T dimension of the vector space is not given. Oh, it is given actually. So it is 5. Dimension of P is 5 because you can see that those degree of this characteristic polynomial, this is 5, so dimension of the vector space must be 5 because T must be some 5 by 5 matrix, otherwise this is not the case, right? So dimension of vector space 5. So let us look what are the possible uh, Jordan canonical form J. So we note that 3 must appear 3 times, and 0. This is x minus 0 and x minus 5, that's why 5 must appear 2 times because degree is 2. So 3 must appear, 0 must appear 3 times, and 5 must appear, the another eigenvalue 5 must appear 2 times. This information is found from characteristic polynomial. Now from minimal polynomial, it is clear that okay, x minus 5, their degree are 1. So the blocks, Jordan blocks corresponding to 5, those will be only 1 by 1. The largest size of Jordan blocks, it is 1, right? So, okay. So this is the Jordan block for 1. So Jordan block for 5. Now, largest size of Jordan blocks for 0, this is actually 2. So 1 Jordan blocks corresponding to 0 must be 2. So let me give the first block as 2. So Jordan blocks means just above the diagonal entries there should be some 1. So this is the Jordan form corresponding to T, and yes, it is clear that this must be uniquely determined from those two information only. So this is not always the case, but some restriction, for example, this is 5 by 5 matrix, those kind of restriction allow me to obtain this form. Otherwise, we may not obtain those forms uniquely by just those two description. Now, so this is true. Therefore, option 1 is true. Now, there are exactly 2 Jordan blocks in Jordan decomposition of 2 T. There are exactly 2. So this is false because Jordan canonical form is uniquely determined, and we can see that uh, there are 1, 2, 3, 4 Jordan blocks. There are 4 Jordan blocks. So this is false. Now the operator induced by T on the quotient space V mod kernel T minus 5i. What will be this? Okay. So from here, let us write the operator. So the operator, the operator will take the form Tx. Let us assume that because up to isomorphism, all finite dimensional vector space are same. So we may assume the vector space as simply some r to the power n. Those kind of thing we can assume, always assume. So T of so let T is a map from R4 to R4. So T x1, x2, x3, x4, or maybe use the column notation. Then it will be more easier. T x1, x2, x3, x4. So R4 means it is M1 by N matrix. I am N by 1 matrix I am taking. So this is same as J of that J times that x1, x2, x3, x4. But this is same as so from here we can see if we just multiply this with x1, x2, x3, x4, then first entry will be 0. So 0 times x01. So the highest top thing will contain x2, then 0 times x2 0, then 0 times x2 0, 5 times. So there will be 5x3 and 5x4. Okay. So it will take this form x2 0 0, 5x3 5x4. Sorry, this is actually 5 by 5 matrix because the operator acting on 5 dimensional. we need to take another x5. So this is actually the operator. So this is actually matrix representation of the operator for with respect to some basis, because the operator may not exactly look like this, but with respect to some basis it will look like this, right? Because Jordan form means what? P inverse, that whatever we have chosen A, P, this will take this form. So that is equivalent to saying there exists some ordered basis for which, with respect to that ordered basis, the operator it will take this form. Okay. Now from here, what we can do? Now the first question is the operator induced by T on the quotient V mod kernel of T minus 5i. Okay. So I have taken V same as R5. Now let us see what is V mod kernel of T minus 5i. First, recall that the quotient space given to vector space V and another W is a subspace of V. Those are vector spaces. Then the quotient space V mod W or V by W, this is defined as, so it will take this form. It will look like those quotients V plus W. This is actually capital W. So this is similar to the quotient group. That if you're familiar with this is exactly the same thing. So V plus W, where some V belongs to that capital V, right? And we can just add, say, in that one class plus, so V dash plus W another class, then addition of those two class, this is defined to be V plus V dash plus W. Similarly, multiplying with some scalar C times this is defined to be CV plus W. So this is actually a vector space. You can look at this. Now we need to see what is V mod kernel T minus 5i, and we need to see that the operator T on this V mod, what is the form of this operator? Okay. So what is first? Let us see what is kernel T minus 5i. So from here it is actually clear. It is clear that kernel of T minus 5i, again we can also look at this. So T minus 5i, this, so this is actually a representation of T, and T minus 5i, this will look like 0, 1, 0, 0, and those are subtracting from those 2 5, it will again give me 0, right? So this is T minus 5i with respect to that same basis. Okay, so kernel of T minus 5i, from here it is clear that kernel of T minus 5i, this is actually 5 dimensional, right? Oh, sorry, we need to subtract 5 from the diagonal, so there will be minus 5, minus 5. So this is actually 3 dimensional, and we also can see from here. Sorry, there is another minus 5. Just subtract from this j. This is same as j minus 5. Okay. Now kernel of t minus 5i, this will contain those kind of vectors. It will take, so rank of this matrix is 3, so nullity will be 2. So there will be 2 linearly independent vectors. So, and we can explicitly see those vector will take this form. So there will be some x3 and x4, and there will be some x5, and other entries are actually 0. So those are actually, so x4, x5 are any scalar. So this is kernel t minus 5i. And now what is v mod kernel t minus 5i? So it will, again, it will look like this, but if we know something like this, if uh, we are not familiar with orthogonal complement, but okay, okay. So without using this, we can write actually. So it will take this kind of, so it will look like those kind of thing, v plus some. So this is actually w in our case. So it will look like v plus w, such that v belongs to v, right? And now our v means all those 5 tuples. V contains all those 5 tuples, right? So it will, again, explicitly, if we write x1, x2 up to x5 plus w, it will consist those kind of vectors. Xi belongs to actually R. But we can see there are only 3 representatives which are linearly independent. One representative will be like this. One, so it is actually spanned by those 3 representatives. 1 0 0 0 0. There is another this plus w, and similarly there will be another 0 1 0 0 0 plus w, and there is another vector 0 0 1 0 0 plus w. This is spanned by those 3, and those 3 are actually linearly independent, because if you take any combination, the linear combination of those 3 things actually does not belongs to this w. So those must be linearly independent, and those 3 actually span the whole w, whole this whole this cosets element, because whatever you just give me anything, for example x1, x2, x3, this representative plus w, then we can write this as x1 times, so suppose this is alpha 1, this is alpha 2, this is alpha 3. So we can write this is as x1 alpha 1 plus x2 alpha 2 plus x3 alpha 3, right? And now you can ask me, what about those x4, x5? Actually, uh, those will be inside this w. Okay, so those two, though those two looks different, but those kind of elements 0 0 0 x4 x5, those kind of elements are actually 0. This is actually 0 in the quotient space. Okay, so as a result, this v mod kernel t minus 5i, this can be taken as this is actually generated by those 3 elements. And let us see what is t applied on alpha 1. So this is actually isomorphic to that 1 0 that is generated by something like this x1, x2, x3. Okay, let me write. This is isomorphic to x1, x2, x3, 0, 0, where xi belongs to R. So this can be thought V mod kernel T minus phi by this can be thought as a subspace of this V itself. Okay, and now let us see what will happen when T applied on this x1, x2, x3, 0, 0. So from this definition, from here, it is clear that there will be some x2 here, there will be some 5x3, 5x2. Okay. So since we have taken x4, x5, those are actually 0, so there will be 0 zeros and only x2 will survive. So it will take this form x1, sorry, there is only single x2, is it? Yes. So we may write it as x2, 0, 0. Okay. So let me denote it by a simpler notation. Just we just work on those blocks and we just remove all those other things. Okay. Otherwise, let me write the same notation. Okay, there is no issue. Okay. So those are actually 0. So again, if we see the matrix representation of T with respect to those ordered bases, this, and these three ordered bases, then it is clear that it will take this form 0, 1, 0, 0, 0, 0, 0, 0, 0, right? This is just this block actually. Okay. So from here it is clear T with respect to alpha 1, alpha 2, alpha 3, this basis. So B equal to this alpha 1, alpha 2, alpha 3. With respect to this order basis, T takes the form this, and therefore it is clear that T is nilpotent. Because now it is clear that T square is 0, therefore T is nilpotent. You can also see this exact fact from here, because if you again apply T on this is same as T on this, but second entry is 0, so it will be 0, 0. So from here it is clear T square is 0. Again, from matrix representation, this is the same fact, and therefore we obtain T is a nilpotent matrix. So this is actually true. The quotient space T, the operator induced or by T on the quotient space, it is actually nilpotent. Now for option 4, let us look what happened when we do the same thing for V mod kernel T, if it is a scalar multiple of identity operator or not. Okay. So let us see what happens when we do the same process on V mod kernel T. So what is V mod kernel T actually? So V mod kernel T, it will take this form. So let us again look what is kernel T. So from here it is clear that kernel T, so rank of this matrix is actually 3, because you can see there are 3 linearly independent uh, rows or column, whatever you say. So rank must be 3. Therefore nullity is 2, and we can see that first row and third row, those two are actually 0 rows. So null space or kernel of T, it can be written as like this. So it is actually generated by kernel T. It is kernel T. It will be generated by those two things. So first and third. So first entry will be 1 and third entry will be 0 0. First and third entries. So those are actually generator of kernel. Okay. Otherwise, you can easily calculate and see those are actually generator of the kernel's T or null space. Now, by the same logic, it is clear that V mod kernel T, this is actually isomorphic to the same thing, similar kind of thing. Actually, this is 0, and so except first and third, we just take other things. So 0, x2, 0, and x4, x5. So xi belongs to R. Now, if we again apply T on this space, then we can see T applied on 0, x2, x4, x5. So this is again we are taking x2, x4, x5, and we just remove x1, x3, right? So if we just remove x1, x3, this will give me, this is, sorry, only this will be removed because x3 is 0. So it will take the form x2 and 0 0, last entry is 5x4. x2 0 0 0, last entry is 5x4. But we can easily see this is not actually a scalar matrix, right? Scalar matrix means diagonal entries are actually scalar, except those things, everything are actually 0. So from here it is clear actually this cannot be possible. Okay, because so we should write this x2, this matrix uh, in terms of this notation. If we can try to write this, so what will be that? So we should actually remove the x2 part from here, because in the spanning thing we have not taken, so above entries are actually 0. Okay. Okay, so this actually belongs to kernel of T. So this is actually automatically 0, because we can write this as x2 0 0 0 5x 0 plus 0 0 0 5x4, right? So this term get cancelled because this belongs to kernel T. So those are actually those actually correspond to V mod kernel T. So those, the corresponding to this class, this is actually 0, because this is same as 100 times x2. So this will be 0, but this is 5x4. So what is the definition of scalar matrix? Scalar matrix means it should be same as scalar matrix means is it C times I? Is it the definition? Yes, scalar multiple of diagonal matrix. So from here it is clear that it cannot be same as, because scalar matrix means C times I. So this is not possible, right? because we can see the matrix representation. If we take the matrix representation, so second corresponding to second and 4, everything is 0, 0, 0, 0, and corresponding to 5, x5, we have 0, 0, 5. So this is not a scalar matrix. This is not equal to C times I. So again, therefore, last option is also incorrect. T, if we take the T restricted on this V mod kernel T, this is not scalar matrix. Okay, then everything is fine. So this is false actually. Only one option 1 and 3 are correct. So let us look at question number 3. Here rank of A is 2, and given that A cube equal to A square, non-zero. And also it is given A is not diagonalized. So what are the Jordan blocks? Okay. So it is given that A cube equal to A cube equal to A square. Therefore A cube minus A square is 0. So if we take this polynomial, so we have this annihilating polynomial. X cube minus x square is annihilating polynomial. Annihilating polynomial. Therefore, minimal polynomial of A. Suppose this is the minimal polynomial. This divides x cube minus x square, right? But this is same as x square into x minus 1. So what are the possibility of minimal polynomials? Minimal polynomial divides this. Therefore, mx may take the form it is either x or x. So those are the forms x minus 1, then x times x squared times x minus 1, and another possibility is x squared, only single x squared. So those are the only thing which divides, those are only monic polynomials which divides this x squared into x minus 1. Okay, but it is clear that those two things, here we can see those two things actually, those degree of x, degree of those individual factors, those are actually 1, right? So multiplicity, if those are the minimal, if suppose this is minimal polynomial, then from here it is clear that Jordan form must take this form, right? 0, 0, 0, 0. 0 is the only eigenvalue, and since minimal polynomial, degree of minimal polynomial is 1, so highest size of Jordan blocks, those are actually 1. Those are one size Jordan blocks. So this is not possible because it is already given A is not diagonalizable. So this is not true. Similarly, x times x minus 1, if we take this also contradict diagonalizability. These two contradict diagonalizability. Recall that if mx is product of product of x minus lambda is corresponding to distinct eigenvalues, then that matrix is actually diagonalizable. So those two are actually diagonalizable, so those two are not possible because it is given that A is not diagonal. Now what is other thing? What is the other thing which is given? Okay, it is also given a square not equal to 0. But if this is the minimal polynomial, this will imply a square equal to 0. Right? So this is also not possible. This is also contradicting. So cancel this. Therefore, mx here is also mx is uniquely determined, and mx takes this form x squared times x minus 1. Okay, because of this square non-zero it is given. Okay. Now, one of the Jordan block of the Jordan canonical form of A. So from here, it takes this form. Okay. Okay. So minimal polynomial, we already obtained minimal polynomial. Can we get the characteristic polynomial chi x? What will be chi x? So again, characteristic polynomial contain those 0 and 1. Now it may happen that x minus there it is degree 4. So those are 0 and 1 are the eigenvalues, distinct eigenvalues. Okay, so without using that fact, one of the Jordan blocks of the Jordan canonical form of A. Yes, so this is true. Option 1 is correct. 1 is correct. Why this is true? Because from here, two, one, so we know that largest size of Jordan block corresponding to lambda, this is same as degree or multiplicity of lambda in minimal polynomial. So we can see here in minimal polynomial that x minus 0, so multiplicity of 0 is 2. Therefore, largest size of Jordan block, it should be 2. So this will appear 0, 0, Jordan block of size 2, J2, 0. This is actually 0, 0, 1, 0. This is the Jordan block of size 2. So this will appear. Right? Now a square equal to A, which is non-zero. Is it possible a square equal to A? So option 2, this is not possible. Why this is not possible? Because a square equal to A, this will imply A satisfies that is annihilating polynomial of A which is x square minus x. an annihilating polynomial, it will be x square minus x. But we see that if this is true, then degree of annihilating polynomial is degree of less than degree of mx, which is a contradiction. This is not possible because minimal polynomial is the smallest degree annihilating polynomial. So this contradicts to the fact annihilating contradict to the fact that annihilating polynomial is divisible by minimal polynomial. This is a contradiction, as this is, so this is not true. Okay. There exists a vector v for which a v non-zero but a square v equal to 0. So since this 0 1 0 0 this appears, so from here it is clear that it should be clear that there will be some vector for which this is true. Okay, because for this we can take the vector 1 0 1 0, and corresponding to this we can just modify with multiplying some p inverse. Okay, so this is actually true. Okay, rank is equal to 2, it is given. So okay, let me write what is the characteristic polynomial. Before option 3, let us see what is the characteristic polynomial. Given rank of A, this is actually 2. Rank of A equal to 2. So minimal polynomial, recall that minimal polynomial is same as x squared times x minus 1. So the characteristic polynomial, so Jordan canonical form is, can we obtain the Jordan canonical form? So it is clear that this should appear. So 1 0 1 0, this block may appear, must appear. Now what are the possibility of other blocks? So there are only two eigenvalues. So eigenvalues are only those two eigenvalues. Sorry, those are the set of eigenvalues are 0, 1. So 0, there are two possibility that one may appear twice. Okay, this is the Jordan block. Otherwise 0, there are two possibility, this or this 0 1 0, sorry, 0 1 0, and now another possibility is 0 will again appear and 1 will again appear. Okay, but if this is the case, then we can see that rank of this Jordan form, this is actually not 2, right? We can see that there are actually 3 linearly independent columns. So rank of this J, rank is actually 1, and here rank is actually 2. So this is true, but this is not possible, right? So Jordan canonical form must take this form, and therefore characteristic polynomial chi a of x, this will be same as, so minimal polynomial must divide characteristic polynomial, so x square x minus 1, and we can see that what will be degree of x minus 1. It is 1, and we also see that 0 appears 3 times in the Jordan form. So dimension of this x, that is dimension of x minus degree of x minus 0, this is actually 3. So this is the characteristic polynomial. Okay, so x cube into x minus 1, which is x4 minus x cube. So this is true. Now we need to see what are, if there exists some vector for which AB non-zero but a square phi equal to 0. So if we see this J, so there exists the vector, take this take phi equal to 0 1 0 0. Okay, so from here it is clear that J phi, this is same as 1 0 0 0, but J square phi, which is non-zero, but J square phi equal to 0 0 vector. Just multiply J twice, so that this block becomes 0. Therefore the calculation give me 0 vector, 0 0 0 0. Okay, so this is actually 4 by 4 matrix. So there is, okay, so this is true, and therefore this will also be true for A, because what is actually A? A is same as P inverse, AP is same as J. There exists some P. Jordan canonical form says J means there exists some P such that this happens, but this will imply A equal to same as PJ P inverse. So there exists some V, and just take, that is modify V to PV. Okay, if we just put PV here, so we'll have A times PV. This is non-zero, but A times A square times PV, this will be 0 because of this fact. A square is same as P J square P inverse, right? Because of this fact, and just multiply PV. This PP cancel, and J square V equal to 0. But JV, here JV will not be 0, and therefore this is actually true. So the conclusion is, therefore option 3 is correct. Option 3 is correct. Some V actually exists. So option 3 correct. AV non-zero, but A square phi is 0. Okay, so let us see question number 4. Here we can see that the matrix, given matrix A, given Jordan canonical form, this is actually same as this. Now the question is, which of the following matrices have the Jordan canonical form this? Okay, so if we see the first matrix for this, let me give the name A1. So first matrix satisfies the condition is A1 square equal to 0, right? It is easy to see that multiply A1 twice. So 1 0 0, it will take the first row, so that multiplying twice give me 0. So A1 square equal to 0. Therefore minimal polynomial of A1, this will be same as x square, because A1 is non-zero, so x cannot be annihilating polynomial. So lowest degree annihilating polynomial, it is x square. And we also see zeros are the only eigenvalues. Okay. So nothing. So it must, minimal polynomial must take some x minus 0 to the power k, and lowest degree for which this annihilates A1, this is actually x square, because x cannot annihilate. So this K must be 2. By the same reason, here also for A2, the same reason we can see A2 of X. This is actually X squared, and similarly A3 of X. This is actually X squared, right? Those are the actually minimal polynomial of A1, A2, A3. We just see that A2 square is 0, A3 square is 0, and those are actually non-zero. And we also there see that characteristic polynomial of A for all those AIs. Let me write it A4. All those AIs, the characteristic polynomial is same as x minus 0 whole cube. That is same as x cube, right? So now for A4, we see that A4 square is non-zero actually. Okay, let me calculate what is A4 square for your convenience. 1 0 0 1 1 0. Just multiply twice so that it becomes actually 0 0 0 0 0 0 and now 1 0 0. So actually F4 cube equal to 0. So minimal polynomial of F4, this is actually x cube, right? Those are actually by similarly. So for F4, the what will be the Jordan block for A4? So let me denote it by J4, corresponding Jordan block, corresponding Jordan canonical form, JC form it is called. So we see that characteristic polynomial forms, characteristic polynomial is x cube, that is 0 is the eigenvalues. So we just put 0 in the diagonal. But here MAX, that is highest degree of 3, highest degree which appears in the Jordan form for this x minus 0 factor, this is actually 3. So the Jordan blocks must be, there exist some Jordan blocks, three size Jordan blocks. So J3 of 0, this should be there. But by this is actually 3 by 3 matrix itself. So Jordan block for this, it will look like this. And similarly for other A1, A2, A3, for A1, A2, A3, JC form, Jordan canonical form, it will be of this form. So there exists, since minimal polynomial of those are actually x squared, so there exists a two size Jordan blocks. So there exists some J2 of 0 and rest of the things are actually determined because only 2 by 2 is already filled, so there is only one vacuum. So just put 0 here. So explicitly it will take this form. There exists a two size Jordan blocks, J2 of 0, which is J2 of 0 means 0 0 in the diagonal, and just put 1 just above the diagonal, and there is another one size Jordan. So from the option it is clear that this Jordan blocks, this appears for 1, 2, 3, but this is not true for question number option 4. Now question 5. Okay. First, A and B are two given matrices. We need to see if those are similar, those are A is diagonalizable or not. B is Jordan canonical form of A. Okay, so let us see what is the Jordan canonical form of A? So eigenvalues of A, those are the set of eigenvalues. It is actually 2, 2, 3. So algebraic multiplicity of 2 is 3. So this is the problematic part. So if we put A minus 2i, then we can see this is same as subtracting 2 from the diagonal 0, 0, 1, and other are unchanged. This is the A minus 2y. So rank of this rank of this rank of A minus 2y, this is actually 2. Therefore eigenspace of A minus 2y, sorry, eigenspace corresponding to 2, lambda equal to 2, it is actually one dimensional, right? So dimension of this eigenspace, this is same as nullity, which is 1. Dimension of this eigenspace or nullity of A minus 2i of A minus 2y. So from here it is clear that geometric multiplicity of 2, this is actually 1 because of dimension of this eigenspace. So this is strictly less than algebraic multiplicity of 2, which is 2. It appears twice, right? So geometric multiplicity less than algebraic multiplicity means it cannot be diagonalizable. So this is wrong. Now let us see what are the other options. Sorry, not diagonalizable, but means option 2 is wrong. A and B are similar over rational. Okay, let us see what is the Jordan form. So Jordan form of A, JC form of A. So there will be two eigenvalues 2, 2, 2. Another eigenvalues will be 3. So this block is already obtained. There is only it is single, so there is only this scalar block. And now we need to see what will be the block. So it can be, is it it will it be separated by two different blocks, or this is the single block? So we can see that from here. Can you see something? Okay, so geometric multiplicity of 2 is actually 1. This means actually there are only one. There will be two blocks. Sorry, geometric multiplicity of 2 is 1. This means number of Jordan blocks corresponding to this 2, it will be actually 1. So if we just separate by two different blocks, then number of Jordan blocks corresponding to 2, it is now 2. Therefore this must be a single Jordan block, right? Since number of Jordan blocks corresponding to eigenvalue and eigenvalue lambda, this is same as geometric multiplicity of lambda. Okay, so this would be the Jordan canonical form for A. Now, so this is correct, right? So this is correct. B is Jordan canonical form of A. The minimal polynomial and characteristic polynomial of A, the minimal polynomial and the characteristic polynomial of A are the same. So we can see that what is the minimal polynomial is already, or characteristic polynomial is already obtained. And what will be the minimal polynomial of A? This is actually same as, there will be one factor x minus 2, another factor x minus 3, and size of this Jordan blocks, this is actually 2. So there will be x minus 2 whole square, because this degree, highest degree of x minus 2, sorry, degree of these factors x minus 2, this determines size of the largest Jordan block. But we can see largest Jordan block corresponding to 2, it has size 2. So degree of this x minus 2 should be 2. Okay, so it is clear that those two are same. Ma x is same as chi x, right? Because what is chi x? Characteristic polynomial. From here it is clear that characteristic polynomial chi a of x, this is x minus 2 whole square times x minus 3. So those two are same. Ma is same as chi a. So this option is correct. Now we need to see if option 1 is correct or not. A and B are similar over rational vectors, rational number q. So we already obtained that this is Jordan canonical form. Therefore, there exists some p such that p inverse AP equal to this Jordan canonical form. So denote it by J. So suppose this is same as J. Okay. So it is clear that A and J are actually similar, but if it is similar over the field of rational number or not. Okay, so let us explicitly see if those are actually similar over rational or not. So here we'll see how can we diagonal, how can we get a Jordan canonical form from a given matrix A. So again, the problematic part is A minus 2y. So for A minus 2y is this, and if we just take A minus 2y whole square, A minus 2y whole square, this will be same as, so second row will become 0, and the first third, there will be only third row. So if we just calculate A minus 2y whole square, this will take this one 0 0 0 0, and the last row will be minus 1 minus 1 1. So now therefore null space of A minus 2y whole square, this is actually generated by those two vectors 1 0 0. Just solve it. Take how can we solve those are clear, right? Those are non-pivot row. Sorry, those are pivot row, and those are actually free columns. So just put one in the first corresponding to first, and another one corresponding to second. So the solution space will be those. Now we can see that 100 is already solution space of this, because 100 times A minus 2y will give me 0. So let us take this to be phi. So something, so this is this 100, this actually belongs to null space of a minus 2y. Therefore, choose v1 equal to 0, 1, 0. Now, what is a minus 2y v1? So, let me copy this a minus 2y from here. Okay. Is there? Okay, there is some. Okay. Okay, so this is a minus 2y and just multiply with v1. v1 means 0, 1, 0. So this will give 2, 0, 0. Right? But this is, give the name v2 for this. This is say v2. So here v1 is, v1, this is chosen because since a minus 2y times v1 is actually non-zero. That's why this is chosen. So v1 is chosen. Now corresponding to that 0, corresponding to the another eigen value 3, we get something like this, right? Just subtracting. So there exists some v3 such that a minus 3i v3 equal to 0. That is v3 is the eigenvector for 3. So from all those data, what we have already obtained. First, we obtained that a times v1. So from here, a times v1 is 2 v1 plus v2. Just rewriting those things. A times v2, it is actually 0 because a times 100 is 0. Therefore, a times 200 is 0. And a times v3, this is 3 v3. So if we put all those data together, we obtain a times v1 block v2. Another third column, let us create another block v3. This is same as 2 v1 plus v2. Then second column, then third column. Therefore, so denoted by some, denoted by q, okay, which equal to q say. So this is same as 2, 1, 0, and then second row is 0, 0, 0, and then third row is 0, 0, 3. Sorry, a times v2 should be 2 times v2, right? Yes. Null space of this a minus 2 v2 belongs to null space of a minus 2y. That means a minus 2y v2 equal to 0. So a v2 is 2 v2. So there I have made a mistake. So a v2 is same as 2 v2. So it will be 2 v2. So from here we can see that this is same as v1, v2, v3. So this is q inverse aq. This is actually the Jordan form, the given Jordan form. We can see this is the given Jordan. And we also notice that those Q, whatever we have taken, those Q and Q inverse, those are actually rational spaces. If Q is a matrix which consists rational entries, then Q inverse is also rational, will consist rational entries. This is easy to see because it is simply we need to take adjoint by determinant, right? So this will be again rational. And we also note that V1, V2, V3, those are actually rational. For example, V2 is this, and what is V1? V1 is this. Another V3, if we just calculate, V3 is also rational. Just calculate it. Therefore, that is actually true that A and B are similar. P inverse, there exists P inverse AB, which is same as this P, or Q inverse P inverse. So though I have written some Q inverse, you can also write P inverse. There is no issue. Okay. So those two, this J is actually given B. This J is the given B. This is same as B given. So P inverse, this is true. Okay. So question number 5 is done. Now let us look at question number 6. Okay, here a square equal to A is given, right? Therefore, minimal a square equal to annihilating polynomial is x square minus x. So minimal polynomial divides annihilating polynomial. So this is again same as x times x minus 1. Therefore, minimal polynomial mx will take one of these forms. It is either x minus 1 or x times x minus 1. Right? The eigenvalues of A. So from here it is clear that eigenvalues this will belongs to either 0, this will be either 0 or 1. So this is true. A is diagonal matrix. So this again, this may not be all 0 and 1, but this can be one of those two things or both. Okay. For example, for here 1 is not eigenvalue, here 0 is not eigenvalue. So those cases may occur. So it is a subset of those two, 0, 1. Now A is diagonal matrix with diagonal entries 0 or 0 and 0 or 1. So from here it is clear that the matrix A is diagonalizable because again those factors, minimal polynomials, it is just product of different factors, and those highest degree of those factors, degrees of those factors are actually 1. That's why A is diagonalizable. So A is diagonalizable, it is clear. But it may not imply that A is diagonal matrix. Okay. For example, take counter example to 2. Counter example for option 2. Take this matrix. A is same as half, 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 half. 2 by 2 matrix. Then we can see that eigenvalues are actually A square will satisfy this formula, right? If we just multiply, it will be half times half. 1/4 plus 1/4, that is half, and similarly all are half. Just multiply. So this satisfies the criteria, but A is not diagonal. So this is false. Not diagonal. Rank of A equal to trace A. Okay, what will be rank of A? So let us see what is the Jordan canonical form. Let J be the Jordan canonical form. Then Jordan canonical form. Okay, do we need Jordan canonical form? Rank of A. Okay, what is rank of A? So let us see what is Jordan canonical form. So it will consist. So for those three possibilities, there can be different Jordan canonical forms. For example, here Jordan canonical forms will be the identity, right? Because those are actually diagonalizable. So Jordan canonical forms will consist some zeros and some one. In this case, all entries will be zero. In this case, all those entries will be one, and there is another case mixed. Okay. So the possible Jordan canonical form, this will be like this. So this will be some 1, 1, 1, and some 1, and some zeros. And those are actually diagonal. That is, J is actually diagonal matrix. It is diagonalizable. I have already told, because those factors, whatever minimal polynomial you choose, the factors actually appear as one. The factors x or x minus 1, those are actually appearing one times. Okay, so product of distinct factors, therefore A is diagonalizable. So Jordan form will take this form. Now, what is the trace of A? Okay, what is trace of? Okay, so we see trace of J is actually same of trace of A. So let me write here trace of A, because what is trace of A? Trace of A is sum of eigenvalues, and so eigenvalues are unchanged by, if we take similar matrices, then they have the same eigenvalues, right? Therefore, their trace will be same. P inverse AP, trace of P inverse AP. This is same as trace of A. This is true because those two have same. They have same eigenvalues. Same eigenvalues including multiplicity. Including multiplicities. This is easy to check, very easy fact. So from here it is clear that their trace are same. Trace of A and trace of J are same, and now trace of J is same as number of this one appears in Jordan form, right? But this is actually same as rank, because this gives me the rank of J, right? But this is actually same as the rank of J. Rank of J. So I should mention the fact that rank can be directly obtained from Jordan canonical form. Just exclude those. Okay, nullity of A can be easily obtained. Nullity will. So let me write the fact. Important fact. Nullity of A. This is number of Jordan blocks corresponding to 0. Okay, so here we can see that nullity will be this thing, and therefore rank should be those 1. And it is also easy to see that that rank of J is, and again rank of J is same as rank of P, rank of A. This is true because rank is invariant under those P inverse AP. P inverse AP and A, those two have same rank because P is, what is P? P is non-invertible matrix. So if you multiply with some non-invertible matrix, rank is actually unchanged. Therefore, this option actually true. Therefore, option 3 is true. Option 3, this is correct. So this is true. Rank of A and the trace of A are same. Now we need to see rank of I minus A and trace of I minus A. Those are same or not. So what is rank of I minus A? So again, if somehow if we can prove that I minus A also satisfy the same criteria, it is done. Because if I minus A satisfy the same criteria, I minus A whole square equal to I minus A, then by the same reason, just replace A by I minus A. So therefore, this will be true, right? So we'll prove this thing that I minus A satisfy the same criteria. So I minus A whole square, this is same as I squared minus I times A, which is A, and there will be another. So it is minus 2A plus A square. But given A square is A, this is already given. Therefore, this is same as I minus 2A plus A, which is I minus A. Therefore, I minus A is also satisfying the criteria that I minus A is actually projection. Those are actually called projection matrix. Okay. So I minus A is also projection. Therefore, rank of I minus A is same as trace of I minus A. This is true. So those are correct options. Okay, let us see question number 7. Here D is the differential operator, that is D will differentiate any given polynomial. Okay, and it is the vector space is polynomial of degree 3, degree at most 3. So the question is which of the following are correct? Okay, so what is D? So P is the space generated by those entries 1x, x squared, x cubed, and x to the power 4. P generated by those polynomials. So linear combination of degree at most 3. So 4 is not allowed. Okay, and if we operate on so D operating D on 1, so what is the differential of 1? It is 0. D of x is 1. D of x square is 2x. D of x cube is 3x square. So if we take this to be a ordered basis B, then with respect to this ordered basis, the metric representation will be D of 1 is 0, means it is just 0 combination. D of x is 1, means it is just 1, 1 times 1. This can be written as 1 times 1 plus 0 times x plus 0 times x square, 0 times x cube, like this. So 0, 0, 0. Just put it in the row. And similarly 2x. 2x means 2 will be here and other are 0. 3x square means 0, 0, 3 and is have I done all those things? Okay, it is actually done. Now the question is if A is nilpotent or not. Can you see if A is nilpotent or not? So it is actually easy to see that A is actually nilpotent. So this is A given. A is the matrix representation. Now, for example, what will be A square? A square means the first row becomes 0, second row will also be 0 because it is 1 0 means take the first row, the combination will be first row. Similarly, next entries will be like this. First two entries are 0, third column will be 2 times the second. So it is 2 0 0 0, and fourth column is 0 0 0 6 0 0. Similarly, we can see that for A cube, it is just 0 0 0 and something non-zero here. Uh, Explicitly, the non-zero thing will be third 3 into the 3 times the second thing, which is 6 0 0 0, like this. Sorry, 6 0 6. This is 0 6 0. Multiply the third column with 3. Oh, third column means 6. Okay, it was okay before. Okay. Even you can see that uh, if you differentiate 3 times x cube, you will get 6 only. So that is what it represents. And therefore, from here it is clear that a to the power 4 is actually 0. Therefore, A is nilpotent. A is nilpotent. A or the operator, both are nilpotent. Now the question is, what is rank of A? From here it is clear that rank of A is A is 3. There are 3 linearly independent rows, columns. So rank of A is 3. A equal to 3. So option 3 is incorrect. Option 3 incorrect. Just remove option 3. Now, A is diagonalizable matrix or not? So we can see that what is algebraic multiplicity of 0. This is upper triangular matrix, therefore 0 is the only eigenvalue, and algebraic multiplicity of 0, it appears 4 times in the upper triangular matrix. So algebraic characteristic polynomial is x to the power 4. Or by the same reasoning, by the same fact, algebraic multiplicity of 0 is 4. But we can see geometric multiplicity of 0. Geometric multiplicity of 0. So what is the nullity of this matrix? Rank is 3, therefore nullity of this matrix is 1. So nullity is 1 means geometric multiplicity of 0 is 1. Right? So again we found that this is strictly less than, therefore this is not diagonalizable. GM is not equal to AM. Those are not equal. So this is not diagonalizable. So this is not diagonalizable. A is diagonalizable, this is false. Now we need to see what is the Jordan form. So from here it is clear that Jordan form will be like this. So Jordan form J. So only 0 is the eigenvalue, so we just put 0 in the diagonal. Now there can be lots of possibilities of blocks, right? For example, those kind of blocks may appear, or those two blocks and there is another block. But we will see those blocks, which is the correct block. So from here, it is we can see that geometric multiplicity of 0 is actually 1. So there, the geometric multiplicity from geometric multiplicity we get number of Jordan blocks. So this means number of Jordan blocks corresponding to 0. This is actually 1, corresponding to the eigenvalue 0. Okay. So there is only one block. So one block means this is the correct Jordan block, right? Which is J4 of 0. This must be 4 size block. So Jordan canonical form is this. Everything is 0 and just above the diagonal there will be 1. Okay, question number 8. This seems very complex question, but it is actually very easy to see. So characteristic polynomial is given this, and minimal polynomial is also given. Now what will be the Jordan block? So 3 will appear twice, 2 will appear 4 times, right? So everywhere this is already given. 3 appears 2 times, 2 appears 4 times. Okay, so we cannot see from here. Now minimal polynomial is x minus 3 and x minus 2 whole square. So this means that multiplicity of this x minus 2 is 2. Therefore, number of Jordan blocks corresponding to 2 will be 2. So number of Jordan blocks corresponding to 2 will be 2. So this one may possible, this Jordan block corresponding to 2. This is also possible, and there are 3 Jordan blocks. So this is not possible. This is not possible. And similarly, there is only single Jordan blocks, right? There is single Jordan block. So this is not possible because of this. And similarly, this is not possible because of this. There are 3 Jordan blocks. Three Jordan blocks corresponding to 2. And similarly, 1 Jordan block corresponding to 2. So that's why those are not possible, because we have already seen that minimal polynomial. From here we get Jordan blocks corresponding to 2. Number of Jordan blocks corresponding to 2, this should be 2. So those two satisfies the criteria for 3 and 4. But number of Jordan blocks corresponding to 3, Jordan blocks corresponding to 3, this should be 1. Right? So corresponding to 3, this is only correct option. So option 4 will be correct. Sorry. I have made a big mistake here. And this, sorry. From here we cannot decide number of Jordan blocks uh, from degree of minimal polynomial. So those factors, it actually gives the size of the blocks, highest Jordan blocks. Sorry for the error. This is size largest size of the largest Jordan block. That whatever I have said, that gives actually the that number of times something appears, number of times Jordan blocks appear for a eigenvalue, that actually gives geometric multiplicity. So whatever I have just said now, that is actually wrong. Sorry. So we cannot apply this reasoning. Size of the largest block is 2. So here the largest blocks is actually 2. So there is no contradiction up to this. There will be contradiction. For option 1 we are getting a contradiction, right? Because size of this Jordan blocks, this has size 2, just size 4, J4 of 2. So this is, that's why this is not 2. Okay, so rest of the for rest of the part, this is actually, there is no contradiction we are arriving at. So those are 2 by 2 size Jordan blocks. Similarly here also, yes. So there is no contradiction up to this. Okay. Jn of 2, this n is less equal to 2, so it is okay. For example, this is J1 of 2, this is J2 of 2 Jordan blocks corresponding to 2. Now for 3, the size should be less equal to 1, right? Because in minimal polynomial, the degree of x minus 3, this factor is 1. So multiplicity of 3, multiplicity of 3 in mx, this denoted by mx, this is actually 1. So multiplicity, we know multiplicity, this is actually same as size of the largest Jordan box corresponding to 1, right? Corresponding to this 3, lambda equal to 3. So largest Jordan blocks which contains 3, it should be its size should be 1. So we can see that, yes. So this is size of this Jordan blocks is 1, J1 of 3. Those are both are J1 of 3. So this is correct. And here is also J1 of 3. Those both are only 1 by 1 matrices. So this is correct. But here this is wrong because size of these blocks, this exceeds 1. This is actually J2 3. So this size 2, it exceeds 1. Therefore this is false. So option 2 and option 3. 2, 3. Okay. Just remember, given a minimal polynomial, from here we can see what is the largest possible Jordan blocks just by looking at those degree. Okay, multiplicity of 2 and multiplicity of this 3. Multiplicity of 3 is 1, multiplicity of 2 is 2. Therefore, the size of Jordan blocks, this is restricted by 1 and 2 correspondingly. Okay, so those are actually not so hard. So let me stop here. Thank you.